Welcome to Delta Wings Aviation Academy, where we prepare you for takeoff.
Hello, pilots. Welcome to Delta Wing Aviation Academy, where we prepare you for takeoff. Today we will be discussing force in descent or glide. Fasten your seatbelts as we prepare for takeoff and get a bird's eye view of the details from the sky. Do you know what these two aircraft have in common? The one on the left is a typical glider, and the space shuttle on the right is also a glider. Most airplanes are able to fly without power for quite some time. Some do it better than others, and in this video, we'll discuss why. In straight and level flight, these are the four forces acting on an airplane when the engine is running. But when thrust is reduced to zero, the drag force is no longer opposed. The rear-facing drag acts to slow down the airplane unless the airplane descends. In a descent, the flight path is now pointed towards the Earth, and the relative airflow opposes this flight path. The airplane is able to maintain its airspeed because a component of the weight force acts in the direction of the flight path. When the forward weight component is strong enough to counteract drag, the airspeed remains constant. In a steady glide descent, lift and drag counteract the weight force. Lift is reduced as the opposing weight component is also reduced. When drag is increased by extending flaps, for example, the angle of descent becomes steeper and glide range becomes shorter. For the airplane to maintain its airspeed, the forward weight component must be greater. Lift is further reduced as the opposing weight component is also reduced. The shallowest angle of descent in best glide range is obtained when there is least drag for the lift required. Thus, the ratio of lift to drag is high. A typical training airplane's lift-to-drag ratio can be represented by a curve like this, and the ratio is 9:1. This means that in still air, this airplane will glide 9 miles of ground distance for every 1 mile of altitude lost. The highest lift-to-drag ratio happens at about 4 degrees angle of attack. If you compare the glider to the space shuttle, you can see that aerodynamically, the glider is a lot more streamlined and has much longer wingspan. We'll discuss these aerodynamic factors in another video. You can see, however, that the space shuttle's low lift-to-drag ratio gives it a much steeper angle of descent and lower glide range. Luckily, the shuttle had a lot of altitude up its sleeve. The angle of attack and airspeed have a direct relationship. We know that the highest lift-to-drag ratio occurs at 4 degrees, but as pilots can't easily tell what the angle of attack is that they're gliding at, airspeed is used instead. This is called the best glide speed, and it gives the airplane best glide range. Should the glide speed increase, the angle of attack will decrease to less than the optimum. The lift-to-drag ratio will reduce, and consequently, the glide range will be shorter. Should the glide speed decrease, the angle of attack will increase. The lift-to-drag ratio will also reduce, and consequently, the glide range will be even shorter.